Hey everyone, I'm Angie, and today we're going to be redesigning a circuit inside of a flashlight to make it better. By improving the product and choosing the right components, we're going to get rid of those pesky hypothetical one-star reviews on Amazon and make a product that people are going to love. Let's get started. Let's pretend you're a product designer and the product that you've designed is a flashlight. So naturally, you used an LED circuit and you picked a resistor to go along with the light. But the customers of your product have left reviews saying that they wish the light was brighter. And I also know that these same customers value the battery life of the product. That makes sense. They don't want to have to constantly charge the flashlight. So, as a designer, it's your job to look at this LED circuit and figure out how to make the light brighter while also not burning it out or wasting battery power. Let's look at the circuit diagram for our LED. It starts at 5 volts, then it went to a red LED, then to a 10K resistor, then to ground. Let's build it now and see if our customers had a point about the light being too dim. So now I've built it, and I'm going to turn the NLAB on to provide power. And now I totally see what the customers are talking about. The light is super dim. This is not a very useful flashlight. It's just not bright enough. Let's fix that. This means we need to pick a better resistor. So in order to pick a better resistor, I first have to figure out how much current this circuit has so that I can up the current and make this light brighter. To do this, we need to start with our foundational equation, V equals IR. Ohm's law, and solving for I, we have I, or current, equals V over R. I'm going to assume that V equals 5 volts, because that's the only voltage that I know right now. I know that the NLAB is supplying 5 volts, and I've got a 10K resistor. So my first guess at the current is 0.0005 amps, or 0.5 milliamps. Now, I've made a lot of assumptions here, and I could be totally wrong. Luckily, I can verify these assumptions using my NLAB. I can use it to measure the voltage here and divide by R to calculate the current. I'm going to connect this point to channel 1. So I can make the invisible visible and see what's happening in my circuit using the app. Okay, I'm going to turn on channel 1 to see what's going on at that point, and I see that the volts per division is set to 1, which means each of these lines represents 1 volt. So my calculation was totally wrong. This point is not reading 5 volts. It's reading 3 volts because 1, 2, 3. There's 3 blocks here. So what's going on here? Allow me to explain using pi. Think of voltage like a delicious pie that you've baked for a party that you're hosting. There's a catch about the pies that you bake, though. You make an awkward announcement to all of your guests that all of the pie must be eaten. No leftovers allowed, ever. Some guests are greedy and cut larger slices than others. And others want to be naughty and have just a sliver. It doesn't matter how big the slices are, just know that all of the pie has to be eaten by the end of the party. So looking at our voltage pi, we know that there's 5 volts of pi here. We used our NLAB to determine the voltage at the halfway point in the circuit, and we saw that there was 3 volts of pi. So that means something, or someone, has taken 2 volts of pi. Nick, that's delicious. No, I'm serious. Okay, so Nick made this pie, and it's so freaking good. That is some good pumpkin voltage right there. Yes. Okay, focus. So that means something on our breadboard is using 2 volts. I'm putting my money on the LED because it's doing something. It's lighting up. If there's something in your circuit that's doing something, chances are it's using voltage because it requires energy to make a beeping sound or read your heartbeat, whatever it's doing. And that checks out because in general, LEDs do require about 2 volts to work. So now there's 3 volts of pi left unaccounted for. And we know that someone has to eat it before we reach ground. The LEDs already had their fill, so who's left? Mr. Resistor! Don't be shy. Have a slice, Mr. Resistor. And you're the only guest left. The rest of my guests left my party because of my weird rule about pies. So you actually get the rest of the pie. All 3 volts of it. Eat it! So now we know there are 3 volts across the resistor, not 5 like we originally assumed. But now we can solve for the actual current going through the resistor. So I equals V over R, which equals 3 volts divided by 10,000 ohms, which equals 0.0003 amps, which equals 0.3 milliamps. This is the current that's making the dim LED. Now I think we should experiment and up the current so that we can make a brighter LED. I'm going to up the current and say that I now equals 1 milliamp. This is my new current. I want to see how bright it's going to be at 1 milliamp. So now let's solve for R. R equals V divided by I, which equals 3 volts divided by 1 milliamp, which equals 3,000 ohms. That would be a resistor that starts with orange, black, red, but sadly, I don't have that in my kit. I do have orange, orange, red, which is 3,300 ohms. Close enough. I won't tell if you won't tell. Let's build it. I'll keep the circuit that I've already built with the 10K resistor and build a new circuit here that allows me to compare to the new resistor. In comparing these two circuits, you can see that indeed this light is much brighter than this light, just as we expected. Not sure if this is showing up very well on camera, but it'll definitely show up at home. But is it bright enough? I'd like to see an even bigger difference. Let's go like 10 times brighter, just to see what that looks like. In order to increase the brightness by 10, we can reduce the resistance by 10. So instead of 3,300 ohms, we'll use 330 ohms. That's orange, orange, brown. Whoa! That is way brighter. But keep in mind, because it's 10 times brighter, it's actually using 10 times more current from the battery. So as a product designer, I'm going to have to weigh, will people be happy about the brightness or will they be unhappy about the shorter battery life? I'll let you decide. Feel free to experiment on your own with any of the resistors that come in your kit. And now you've gotten a taste of how product designers and engineers work behind the scenes to create the products you love. Speaking of taste, babe, did you try this? Nick,
Yeah.
come get some. Come eat with me. Okay, I'll be the LED and you be the resistor. So you get 3 volts and I get 2 volts.
Good.
Cheers. Is that not good?
Delicious.
Now you have to eat that entire thing, you know.
Sounds good.
You're not gonna argue?
Why would I argue?
I wanted to say something like, I don't make the rules, man. It's the rules of physics.
You want me to say that? I have to eat this whole thing?
You do. I don't make the rules of physics, man. You gotta finish the pie. I don't think it's gonna be too difficult.
Nope. I'll be back in a minute.
Until next time, I'm Angie. Thanks for watching.